This is a video from section 7.2 in Calculus 2. The directions say to evaluate the integral. Let's take a look at problem 1. Suppose we have the integral of sine cubed x times cosine squared x dx. Now, notice how the power of the sine is odd. And so I want to rewrite this integral as follows. So sine cubed x can be written as sine squared x times sine of x. And then I'm just going to write cosine squared x as it is. Now, from here, remember that sine squared x is equal to 1 minus cosine squared x. And so this is the integral of 1 minus cosine squared x. And if you don't mind, I'm going to write cosine squared x, right? So I get 1 minus cosine squared x times cosine squared x times sine of x dx. Why would I do that? Because the derivative of cosine of x is negative sine x. And so we can solve this by way of u substitution. So I'm going to let u equal cosine of x. du is negative sine x dx. And so sine x dx is equal to negative du. From here, this is negative the integral of 1 minus u squared times u squared du. So this is negative the integral of u squared minus u to the fourth du. Now, if you want, you can distribute that negative inside, and you can rewrite this as the integral of u to the fourth minus u squared du. And so this is 1/5 u to the fifth minus 1/3 u to the third plus c. Now, let's go back. What is u? U is cosine of x. So from here, we can say 1/5 cosine to the fifth x minus 1/3 cosine cubed x plus c. And that's how we do problem number 1. Let's take a look at problem number 5. Suppose we have the integral of sine to the fifth of 2t cosine squared of 2t dt. Okay. Notice how the power of the sine is odd. And so we want to rewrite this integral in the following way. Now, sine to the fifth 2t is sine to the fourth of 2t times sine of 2t. It's just another way to write sine to the fifth of 2t. And we're going to multiply that by cosine squared of 2t dt. Now, don't forget, sine to the fourth of 2t is sine squared of 2t squared times cosine squared of 2t times sine of 2t dt. But isn't sine squared of 2t 1 minus cosine squared of 2t? So I'm going to rewrite this as 1 minus cosine squared of 2t squared times cosine squared of 2t times sine of 2t dt. From here, I'm going to let u be cosine of 2t. So du is negative 2 sine of 2t dt. That's just chain rule. But don't forget, we need to solve for sine of 2t dt. So sine of 2t dt is negative 1/2 du. Okay, from here, I'm going to pull the negative 1/2 out in front of the integral, and then I'm going to take 1 minus u squared to the second, okay? And then I'm going to multiply by u squared, and I'm going to integrate with respect to u. So this is negative 1/2 of, or times, the integral of 1 minus 2u squared plus u to the fourth, and then this is times u squared du. Now I need to distribute that u squared inside. So this is negative 1/2 the integral of u squared minus 2u to the fourth plus u to the sixth du. I hope that's okay. Now we need to pay attention to what our u is. That's up here. Now, from here, this is negative 1/2 of. Now, I integrate. So I get 1/3 u cubed, right? And then from here, I get minus 2/5 u to the fifth. Then I'm going to go plus, and then from here, it's 1/7 u to the seventh. And then I'm going to add c. I can distribute that negative inside. So I get negative 1/6 u to the third plus 1/5 u to the fifth minus 1/14, right? U to the seventh plus c. But don't forget, u is equal to cosine of 2t. And so this is negative 1/3, this is negative 1/6 cosine cubed of 2t plus 1/5 cosine to the fifth of 2t minus 1/14 cosine to the seventh of 2t plus c. And that's how we do problem number 5. Let's take a look at problem number 9. So on problem number 9, we have the integral from 0 to pi of cosine to the fourth of 2t dt. Okay? Now, the power of the cosine is even. So what I'm going to do is I'm going to write this as the integral from 0 to pi of cosine squared of 2t times cosine squared of 2t dt. Okay? Now, I'm going to do the power reducing formula. That's really important, and again, from class, I really want to stress that we know how to do that, okay, and know how to do that well. And so this is going to be 1 plus cosine of 4t, okay, divided by 2 times 1 plus cosine of 4t divided by 2 dt. Now, I'm going to pull the 1/4 out in front of the integral, and then I'm going to integrate from 0 to pi of 1 plus cosine of 4t times 1 plus cosine of 4t dt. So notice I'm really trying to go just step by step. Okay? From here. So this is 1/4 the integral from 0 to pi, and I'm going to get 1 plus 2 cosine of 4t plus cosine squared of 4t dt. Now, we're going to need that power reducing formula again, okay? And so from here, we get 1/4 the integral from 0 to pi of. Now, I'm going to get 1 plus 2 cosine of 4t plus, and then it's 1 plus cosine, and then I'm going to double this angle here. So I'm going to get 1 plus cosine of 8t divided by 2. And then I'm going to integrate with respect to t. Just one step at a time. And now for that third term, I'm going to split the fraction. So I get 1/4 the integral from 0 to pi of 1 plus 2 cosine of 4t plus 1/2 plus 1/2 cosine of 8t dt. Now, remember 1 plus 1/2 is 3 over 2. Okay? So from here, I'm going to get 3/2 t. Because again, don't forget 1 plus 1/2 is 3/2. Then I'm going to go plus. Then I'm going to integrate this guy here. That's going to be 2 over 4 sine of 4t. Then I'm going to go plus 1/2 times 1/8 sine of 8t. So remember, we're going backwards now, okay? And then I'm going to evaluate from 0 to pi. Okay. From here, I'm going to get 1/4 the quantity. If I plug in pi, I get 3 pi over 2. And I'm plugging in pi for t right here. Now, sine of 4 pi is 0. Sine of 8 pi is 0. So we're done. And if I plug in 0 here, 3/2 times 0 is 0. Sine of 0 is 0. So I'm basically subtracting 0. And so the correct answer here should be 3 pi divided by 8. Okay, and that's problem number 9. Let's take a look at 13. On 13, we have the integral of the square root of cosine theta, right, times sine cubed theta d theta. The power of the sine is odd, and so I need to save a sine of theta. So what I'm going to do is I'm going to write the integral of the square root of cosine theta times sine squared theta times sine of theta d theta. But remember, sine squared theta is 1 minus cosine squared theta, okay? Because what am I trying to go for? I'm trying to go for a substitution that will get rid of all the thetas. That's the goal. So I have the square root of cosine theta times 1 minus cosine squared theta times sine of theta d theta, okay? And I'm going to let u equal cosine theta. du is negative sine theta d theta. So sine theta d theta is negative du. And so this is equal to negative the integral of the square root of u times 1 minus u squared du, right? So wherever I saw a cosine theta, I popped in a u. And so from here, I get negative the integral of square root of u minus u. Now, the exponent is 2 plus a half, right? And that's 5 halves du. And so I'm going to distribute that negative in, if you don't mind, and I'm going to write this as u to the 5 halves minus u to the 1 half du. Now, don't forget, 5 halves plus 1 is 5 halves plus 2 over 2, right? You get 7 halves. And then 1 half plus 1 is 1 half plus 2 over 2, and that's 3 halves, okay? And so what do I get? I get 2/7 u to the 7 halves minus 2/3 u to the 3 halves plus c. But remember, u is cosine of theta. So remember, we can go back here. U is cosine theta. And I'm done. So this is 2/7 times cosine theta to the 7 halves minus 2/3 times cosine theta to the 3 halves plus c. And that's how we do problem number 13. Let's take a look at problem number 17. So on 17, we have the following. We have the integral of cotangent x times cosine squared x dx. Now, something to keep in mind here, okay, before we try to attack this problem. The way trig functions are paired off, typically speaking, is like I'm going to pair them off this way. So cosine of x gets paired off with sine of x. Tangent x gets paired off with secant x. And then cotangent x gets paired off with cosecant x. But cosine x and cotangent x typically don't get paired off. And so my gut reaction when I see a problem like this is I'm going to take cotangent x and I'm going to write it as cosine x over sine x, because sines and cosines go together really nicely. And then I'm going to multiply by cosine squared x dx. But your goal is to do a substitution, and we can't do that in its present state. But we can do this, though. I can take cosine x over sine x and multiply it by 1 minus sine squared x. Do you agree? Because look, u is sine of x. Du is cosine x dx. And it's really slick. Now, cosine x dx is going to become du. So this is the integral of 1 over u times 1 minus u squared du. See? Sine of x gets replaced with u, but that sine of x is in the denominator. So if I distribute in, I get 1 over u minus u du, and I'm done. You get natural log of the absolute value of u minus 1/2 u squared plus c. But remember, u is equal to, let's remind ourselves, u is equal to sine of x. And so, let me put sine of x here. So this is natural log of the absolute value of sine x minus 1/2 sine squared x plus c. So please let me know if that's okay. I hope that makes sense. Let's see if we can fit in another one. So let's take a look at problem number 21. And this is the integral of tangent x times secant cubed x dx. Now, I just happen to know that the derivative of secant x is secant x tangent x, right? So the power of the secant, notice that the power of the secant is odd. That's good, right? Because I'm going to write this as tangent x times secant x times secant squared x dx. From here, u is secant x, du is secant x tangent x dx. And so this is the integral of u squared du, which is 1/3 u cubed plus c. But u is secant x. So this is 1/3 secant cubed x plus c. And that's how we do problem number 21. Let's take a look at 23. Suppose I have the integral of tangent squared x dx. There's a few ways to attack this problem, right? I don't have an immediate elementary antiderivative of tangent squared x, but I do have an immediate elementary antiderivative of secant squared x. And so a slick way to do this problem is to take tangent squared x and write it as secant squared x minus 1. And then I'm done, right? And so this is tangent x minus x plus c. That's it. That's how we do 23. Let's take a look at 25. Suppose we had the integral of tangent to the 4th x times secant to the 6th x dx. Here's how I would attack this problem. Notice how the power of the secant is even. And so what I want to do is save a secant squared x out of this. And so I'm going to write this as the integral of tangent squared x, if you don't mind, raised to the second, okay, times secant to the fourth x times secant squared x dx. In fact, we can do even better. We can just leave that as tangent to the fourth x. I'll explain why in a second. But we do have to mess with that secant to the fourth x. So this is the integral of tangent to the fourth x times secant squared x raised to the second times secant squared x dx. Okay. From here, we get the integral of tangent to the fourth x times 1 plus tangent squared x, right? That's a trig identity that we have to know well. So we get tangent to the fourth x times 1 plus tangent squared x to the second times secant squared x dx. Now remember, the derivative of tangent x is secant squared x. So if u is tangent x, du is secant squared x dx. So this whole entire thing is going to become du. Okay? And so this is the integral of u to the fourth times 1 plus u squared to the second du. So we get the integral of u to the fourth times 1 plus 2u squared plus u to the fourth du. Distribute this u to the fourth inside. And we get the integral of u to the fourth plus 2u to the sixth plus u to the eighth du. And then I'm done. We get 1/5 u to the fifth plus 2/7 u to the seventh plus 1/9 u to the ninth plus c. But let's go back. What is u? U is tangent x. So if we want to finish this off, you get 1/5 tangent to the fifth x, right? Plus 2/7 tangent to the seventh x, right? Or tangent x to the seventh. Then I'm going to go plus 1/9 tangent to the ninth x plus c.
Hello.
And that'll do it for this video for section 7.2.
Hello.
Okay, so again, this is a video from section 7.2. We did problems 1, 5, 9. We did 1, 5, 9, 13, 17, 21, and 25. And again, I apologize. That was my son in the background. If I don't want to redo this video. All right, thank you.